Thank you so much, Ophelia, and good afternoon, everybody. First of all, thank you so much for coming and tuning into this talk. So, as you've heard, I'll be giving a presentation this afternoon about how we, colleagues and myself within the Event Horizon Telescope collaboration were able to take the first image of a supermassive black hole. And in fact, actually, we've taken two images now. We've taken one of the supermassive black hole in the heart of the galaxy M87, and more recently, in fact, just last year in May, an image of the supermassive black hole in the center of our own galaxy. And so I'll actually be talking about both. And this image you see here on the title slide, this is actually a supercomputer simulation I made of what the black hole at the center of our galaxy would look like if we had infinite resolution. And I've taken some creative liberty with the color scale, and I've put some stars there. You wouldn't see stars, but it's an accurate representation of how the matter would be streaming onto the black hole. You see a bright ring, you see a very dark center where there's an absence of any emission, including the stars, and that's where the event horizon of the black hole lives. And my hope is that by the end of this talk, I've been able to convey to you some sense of what this image means, and you'll be able to look at it and know what its features are and what it's telling us about the black hole. So without further ado, I'm going to jump straight in. So this talk is actually a talk about two black holes, as I've mentioned. So the first one that we saw in 2019, actually, is the supermassive black hole in the heart of the galaxy M87. So that's short for Messier 87. So this is the giant elliptical galaxy Messier 87. So whenever I say M87, I'm referring to this black hole and that particular galaxy. And of course, a few years later, so just last year, we published the first image of the supermassive black hole in the heart of our galaxy. And we call this one Sag A star for short, so Sagittarius A star. So when I say Sag A star, I refer to this black hole. And this was published 3 years later. And so in my talk today, I'll talk about the physics of these, what these images mean, what the uncertainties are, how we actually went about producing these images, and the theoretical and observational techniques involved, and why these images are actually so remarkable. Because these are, you could say, oh, well, they're just two bright, blurry donuts. What do I learn from this? Well, it's actually quite remarkable that they're both bright, blurry donuts, so to speak, because they're very different black holes. The one on the left, M87, has a mass of around 6.5 billion times the mass of the sun. The one on the right, Sagittarius A star, has a mass of around 4 million times the mass of the sun. So there's actually a factor of over 1,500 in their masses. And yet morphologically, those images appear very similar. So you see a bright annulus, like a thick ring. You see a very dark center, which we call the central brightness depression, and that precipitous drop in flux that you see in the center, we believe to be consistent with the event horizon of the black hole. You see the image is asymmetric in brightness. That's because the black hole is probably spinning. So the material that's spinning towards us appears brighter because it's Doppler boosted. And conversely, the material which is spinning away from us appears dimmer, and it's Doppler boosted away from our line of sight. So these images were actually produced by recording data from the telescopes that we have within the Event Horizon Telescope, or EHT Array, back in 2017. So we recorded the data in 2017 for both of these black holes, published the first set of data for M87 in 2019, and the second set in 2022. So you can see there's a long lead time there between actually recording the data and finally producing images and publishing them. So there were 8 telescopes involved, which you see here listed on the right from top to bottom. And you can see these white lines on the left of the sort of projection of the globe. And the white lines indicate the baselines, or the connections between them, the sort of distances. And of those 8 telescopes, the first 7 from top to bottom were involved in both sets of observations. And the bottom one, yes, the South Pole Telescope, because of course, its geographical location in the south of the southern hemisphere, it was only used to record data for Sagittarius A star because of course, M87's position in the sky is such that the SPT can't observe it. So these were the telescopes that were used in the array at the time. But the EHT is more than a network of telescopes. It's actually more importantly, a network of scientists, engineers, philosophers, and by scientists, of course, I mean many areas of science. So we have astrophysicists, we have theoretical physicists, we have data scientists, and so And we've all been working together for many years, and this is just a subset of all of us here at our December 2018 meeting in Nijmegen in the Netherlands. So we had the data at this point. We're all smiling because we know what it looks like and we haven't published it yet. The following year, we had a meeting in December after we published the first black hole image in Hawaii. And I always joke that our budgets have been upgraded a little bit since then. So, you know, we were able to all travel to Hawaii, and this is us just before Christmas. So we meet regularly, and we're very active collaboration. We're very diverse, and we come from, I think, over 200 different institutes spanning almost all the continents on Earth. So, and this is us most recently at an in-person meeting in June in Granada last year, and we'll be meeting actually again in June this year in Taiwan. And hopefully there'll be more of us this time because the COVID restrictions will have relaxed even further. So coming back to the science, I've shown you that, you know, this really is an enormous collaborative effort which underpins producing these images. You know, it's decades of work that's gone into this, both in terms of the science and developing our understanding of black holes and how Einstein's theory of gravity, general relativity, which we'll touch upon later, actually describes them and how light moves around them and what we can predict that we see, but also the technological side of things. So how do you build instruments which can produce these sorts of images? How do you connect telescopes across such vast distances and so on? So, you know, there have been a lot of people who've been working on this for a very long time, and we are in the very fortunate position today where this technology has matured to the point where we can produce these sorts of images. So before getting into the science, I wanted to show a few memes, and I always do this. So it's the sort of Lord of the memes. And the first one you see here, of course, is the Eye of Sauron. And those of you who are into your comics know that this is Peter Parker. And he sees a blurry image, and now he sees the Eye of Sauron. So this one went around straight after the image was published in 2019 on social media. Another one, which was quite popular, I think, in North America, because they woke up at their breakfast time to see this image, is the giant cosmic bagel. So we have fear, we have food, and my favorite is the one felines. So we have these fundamental tenets of human nature reflected in these, I think, really cool social media interpretations, if you will, of what these black hole images mean. Of course, this is two black holes, and this wasn't strictly correct at the time because there's only one, but of course we've seen two now. But all joking aside, what these things show is that, you know, that the concept of a black hole and a ring of light around a cosmic abyss, I think, you know, these sorts of notions and concepts, they really resonate with people in many different ways. So now coming back to the main talk itself, this was, of course, the first black hole image. And we went further and we produced the second one. So this is the one of the black hole in the center of our galaxy. Just on 12th of May last year, we published this. And you see it's morphologically very different. There's actually three bright blobs. And at the end of by the end of the talk, hopefully I'll have explained why there are three bright blobs. It's basically because we don't know where that bright emission is. It could be in potentially one of those three places. And those blobs represent our uncertainty and the structure within that ring. So we're confident about the thickness of the ring and its diameter. We're not so confident about the structure within it. And that's very much in contrast to the previous black hole, M87, where we're very confident. And I'm going to go into that shortly. So first of all, I wanted to start with a quick overview of supermassive black holes, so astrophysical supermassive black holes. So a very brief history, and I'll go through this actually quicker than I usually do because there's some more important stuff that we have to get to this afternoon. But if we draw a timeline, the actual history of black holes goes back all the way to the 18th century, actually. And this is something I only discovered recently, after 2019, that there was an English polymath by the name of Reverend John Mitchell, who proposed the notion of an object called a dark star. So he was playing around with Newton's theory of gravity, which was, of course, the prevalent theory of gravity at the time. And there's a notion of a light particle or corpuscle. And he basically posited the notion of a dark star by formulating a concept. He said, let's take a concentration of mass, think of it as like a spherical distribution of mass, like a star, and we keep compressing it. So we keep increasing its density, shrinking its radius, until the escape velocity of a particle, a light particle from the surface of that star would actually be the speed of light. And therefore, of course, at that point, if the escape velocity is greater than the speed of light, then light produced by that star couldn't escape it couldn't be radiated away from the surface. So that star would be formally dark because we couldn't see it. And so this is actually, in a sense, a sort of proto-black hole. And it's a concept really which predates Einstein's theory of general relativity by more than a century, which is quite remarkable. And Pierre-Simon Laplace actually also came up with the same concept independently about a decade later. But this fell out of favor very quickly because Thomas Young showed his double slit experiment, where you see the diffraction patterns of light through a double slit, and you also see the interference patterns. And at the time, people thought, well, light can't be a particle, it must be a wave. And of course, it wasn't until quantum mechanics in the early 20th century that issue was reconciled, and the so-called wave-particle nature, the duality of light was established. So anyway, fast forwarding to 1915, Einstein published his general theory of relativity, which is a geometrical theory of gravity, which we'll come to soon in the slides. And it's a remarkable theory, and the equations, the Einstein field equations, are so complex that no one thought they would be solved. But actually in the same year, Karl Schwarzschild found the solution for a static star, a non-rotating star, which we'd later come to know as a black hole, a Schwarzschild black hole. And he published this in 1916 and sadly died shortly thereafter, but that was the first solution. Over 50 years of work went into studying this and other solutions, and including solutions which actually had spin. So these would describe black holes with a spin as well as a mass. And, you know, people like Stephen Hawking and Roger Penrose and many other important black hole physicists and mathematicians were developing the theory and checking about these issues to do with the singularities and whether the event horizon is a real singularity or not, and so on. So this is a lot of foundational work which we don't have time to go into this evening. But by 1967, John Wheeler, who's an American gravitational physicist at a meeting of the American Astrophysical Society, coined the phrase black hole. And that term stuck. And I always talk about this in my talks, and I say that it's actually a little bit misleading, because a black hole isn't black, because you've probably heard of Hawking radiation. So a black hole can radiate away a minuscule amount of thermal energy. So actually it's not black, and it's not a hole because you can't fill a black hole. The more matter you dump into it, it actually grows. So it's not formally a hole either. So it's a term which has stuck, but it's actually a little bit misleading. But nonetheless, that phrase is how we refer to them today, as a vacuum solution to Einstein's field equations. So in the 60s and onwards, there was a lot of indirect evidence. So we've seen, for example, stellar mass black holes stripping away matter from a nearby star. So these are so-called high mass X-ray binaries. And Cygnus X1 was one of the first that was detected. It was very bright in the X-rays, and that's how we first detected it. But they're very bright actually across the entire electromagnetic spectrum. We've detected compact objects like pulsars. So Dame Jocelyn Bell Burnell actually first discovered these. And we've seen the motion of stars in the center of our galaxy. And these are stars moving in incredibly eccentric orbits. So they're not planets, they're not meteorites or anything like that. These are actual stars moving in highly eccentric orbits about a common center of mass in the central nuclear region. So there's a lot of evidence to suggest that black holes are out there in the universe, because they could really only be the only real explanation for what's powering these incredibly energetic phenomena and processes, and driving these incredibly, bizarre dynamical processes that we're seeing, for example, in the center of our galaxy. But of course, that evidence was indirect. Now, in 2015, of course, there was the sensational discovery of gravitational waves. So there was a detection, GW 150914, if I recall correctly, the number. It was the merger of a binary black hole. So a pair of black holes, one of mass around, I think, 29 solar masses, the other around 36. And these two black holes were observed to merge and form a single black hole. And there was a beautiful gravitational waveform of this. And this was the first observational confirmation of gravitational waves. And of course, many more detections by the LIGO-Virgo-CAGRA collaboration have been made since, including of binary neutron stars as well. But this was really important because it established that Einstein's theory actually does include gravitational waves as a fundamental component. So this was something that has been understood to be possible theoretically for decades. And Einstein himself was very skeptical about this, but the theory allowed for them. And in fact, they've now been detected, and they provide a beautiful window onto the universe. And we can sort of listen to the universe as it echoes with the violent collisions of these things and not just see them. Anyway, so moving on, Coming back to black holes themselves, in 2019, of course, we took the very important step of creating the first image of a black hole with the Event Horizon Telescope. And I put this image in quotation marks because, of course, it's not truly an image. It's a reconstruction from multiple radio telescopes, which I'll describe soon. But nonetheless, it's a meaningful representation of what that hot plasma around the black hole that's falling onto the event horizon looks like. And this is the first time we've ever seen a black hole. And we, of course, we did the same again in 2022 with our own supermassive black hole, Sagittarius A star, at the heart of our galaxy. So now, you know, it's basically been a long journey getting to a point where we can just about start to spatially resolve the matter around the edge of the event horizon. And this is the start, really, of a very exciting new field. And in the next few slides, I'm going to explain a little bit what these images mean and then how we actually produce them to begin with. So we've known for a long time with both of these black holes. So coming first to the M87 black hole in the galaxy Messier 87. So as early as 1918, an astronomer called Curtis actually saw in the optical an image like this on the left of a very bright core and a straight, as he described, a straight curious ray emanating from the core. And you can see that this curious ray, as he described it, which is we now know to be a relativistic jet of plasma that's being shot out from that central region where the black hole resides, is actually much, much larger even than the extent of the galaxy itself. It's absolutely enormous. So whatever's powering this, you know, this is monstrously powerful. And there would actually be two jets. We understand them from the theory to be bipolar. So there would be one moving in the other direction, but this jet is almost oriented towards us along our line of sight. So the counter jet is actually very dim and you don't see it at these wavelengths. But in the right image here, you can see an evacuated region and a termination shock to the top of the image. And that's where we believe that counter jet is actually colliding with, it slows down enough that it can be collide with the ambient medium and produce that emission that we see there. So you see the main jet that's going into the sort of southeast direction, and you see the counter jet going in the other direction. And you see this thing across enormous spatial scales. And actually, so these images from top to bottom in the center here, they zooming in successively smaller scales, actually 6 orders of magnitude, so a factor of million between the top and the bottom. So over the years, we've been able to push to higher and higher frequencies with the light that we're looking at. And we've been able to zoom in the core of M87 from top to bottom here. And finally, what we've been able to do in the last few years is actually resolve the very core. And we see a bright ring, which is coincident with a black hole. And actually, it's a black hole which produces that. And the theory, Einstein's theory, predicts these bright rings. And their particular diameter is proportional to the mass of the black hole. And we actually did find that this ring's diameter is consistent with the mass of the black hole too. So it's really quite beautiful that we're now able to zoom in to such an extent that we can see the matter at the very edge of the event horizon. And Sagittarius A star actually is a very different beast. So there have been observations for a very long time by two leading groups. So the group at UCLA led by Andrea Getz and the group in Germany led by Reinhard Genzel. And this is a movie of the observations from the Keck telescope, which is basically using near-infrared astrometry to track the motion of stars, the orbital motion of stars around the center of our galaxy. And there's a dark region that can't be resolved, about which all of these stars that you see, these beautiful elliptical trajectories, move around this common center. And you're able to use Kepler's laws, you're able to use some nice statistical methods to combine these different data, and you can actually infer a mass of that central region of around 4 million solar masses within a region smaller than the orbital radius of Mercury. So there's a lot of mass in a very small place, basically, a very small space, excuse me. So this is very important because it's telling you that the center of our galaxy, there's a distribution of mass, and it's so dense it can only really be a black hole in a very, very, very small finite volume. And actually, this was enough. There were obviously decades of observations which led up to this, but this actually earned half of the Nobel Prize for Physics in 2020 for this discovery and for this measurement. And actually, this measurement is very precise. I think it's 3 significant digits of precision, which is really quite something, especially for astronomy. So now I think hopefully you've convinced you that there's been a lot of evidence for the existence of black holes, and that's provided a lot of motivation to build these kinds of telescopes and conduct these kind of observing campaigns. Now let's shift our focus a little bit more towards the physics of these objects and what we can learn from these images and how we can interpret them. So I think the best place to start is to actually ask the question, what is a black hole? Now, the honest answer is we don't really know. And as far as we don't know what that object is, what it's fundamentally comprised of, and so on. But what we do know is how it behaves, and how we have a good understanding of how matter seems to move around it and what's happening near the edge of the black hole. So we formally understand a black hole to be a very, very compact object. So if you took any spherical object of radius, we call it big R, and so if you look at the figure here on the left, and you compress that radius down. So you keep compressing this sphere of matter until its radius is now the same radius as this RSCH, the Schwarzschild radius. Then that object will formally collapse and form a black hole. So thinking of this another way, it's like saying if you take the sun and you compress our sun down to a radius of smaller than 2.95 kilometers, the sun would collapse and form a black hole. So you'd have to compress all of that mass into a very small radius. And you could even do this with the Earth. So you could take everything on the Earth and you could compress the entire Earth into a sphere of, I believe of radius, or maybe diameter, I have to double check, but around 8.8 millimeters. So if you could compress the Earth down to 8.8 millimeters, then it would collapse and form a black hole too. And because that is the Schwarzschild radius of the Earth. So you can see that a black hole is incredibly dense. They are very, very compact objects, and they're so compact that light can't escape them. But we can't see a black hole because you've heard about the event horizon, but we can see what's going on at the very edge of the event horizon. And so there's a few interesting things that are going on around a black hole. But I think the first thing is we should actually look at the theory. So that's the general theory of relativity from Einstein and see what it tells us. So if you asked Einstein what a black hole is, he'd say it's a vacuum solution to these equations here. And these equations are nasty, and we're not going to go into them. I'm just going to approach them from a phenomenological perspective and say that this left-hand side you can think of as space-time. So this is Einstein's wonderful concept that space and time should be treated on an equal footing and woven into this 4-dimensional fabric, which we now refer to as space-time. And everything in the universe, all of the matter, and that includes us, stars, dust, gas, lives within this space-time. And the two are proportional to one another, and so there's a dynamical feedback. And so Einstein's theory tells us that, for example, the gravitational force, unlike in Newton's theory, it isn't action at a distance, it's a consequence of the curvature of space-time. So things feel a gravitational force because space-time is curved around that object, which the smaller object is gravitating towards. And so gravity causes the distribution of matter to change. So you can see in this equation that if you increase the curvature of space-time, then you can increase the density of matter. But conversely, you could compress matter like we were talking about earlier, and that would lead to a local increase in the curvature of the space-time within which that matter lives. And so it's a dynamical thing, and there's a feedback. So it's very bizarre, and yet it's a theory which is remarkably well tested, at least in certain regimes, and it's passed every single test, and our lives fundamentally are dependent on this theory. For example, GPS systems wouldn't work without this theory. And black holes themselves actually are a solution to these equations when the right-hand side is 0. So if there's no matter, then you have what's called a vacuum solution, and that's a black hole. And black holes can be characterized in terms of just 3 parameters: their mass, their spin, so how rapidly they rotate, and their electric charge. And actually you can neglect electric charge because the black holes have a lot of matter around them. And so very quickly they reach charge neutrality with that matter. So just the first 2, the mass and the spin, are enough to describe, we believe, if Einstein is correct, every black hole in the universe, which is absolutely remarkable. So they are perhaps the most simple macroscopic objects in the universe. So moving on from their basic properties to how they interact with the environment. First of all, I wanted to say actually that you've heard of this fabric of space-time, and it's very important that we consider these sorts of notions because, for example, you can have a star and the true location of that distant star would be at a point A you see in this figure on the left at the top of that panel. And if you don't consider the curvature of space-time, for example, around the sun, so let's say we're on Earth and we're observing a distant star, which is actually formally behind the sun at that point in time, we would infer that its presence be at location B because we assume light travels in straight lines. But in fact, in Einstein's general relativity, which is a geometrical theory of gravity, light travels on the straightest possible lines within that curved space-time. So it's formally a straight line, but it's what we call a geodesic. It's the straightest possible line within that curved fabric of space-time, and it would actually follow the trajectory A. And actually, that's been tested to exquisite precision and found to be true. So we've seen, for example, the deflection of starlight during solar eclipses, for example. And it's been found that this is correct, and actually you need Einstein's theory. So Einstein's theory and this notion of space-time actually supersedes the Newtonian theory of gravity, and it's predictive in regimes where, for example, like you see here, where Newton's theory completely fails. So it's a very powerful theory. So black holes themselves, changing tack a little bit, have a few different interesting things going on around them. So you've all heard of the event horizon. This is the point of no return. So you'd have to travel at the speed of light if you were at this boundary. It's not a physical boundary. It's a sort of mathematical boundary or a membrane. If you cross that boundary, you'd have to travel faster than light. And as we know, nothing, as far as we know, can travel faster than light. And so that is a true horizon. It's a true causal boundary. Anything which passes that boundary within it will never escape, and we can never see past it, and we'll never be aware, according to the theory, of what's going on inside. And so, of course, unfortunately, hiding within that boundary, within the event horizon, is the singularity, where the equations blow up and formally the black hole has a sort of infinite curvature. And that's a big problem, which I'm not going to talk about, but it's a big issue. And it's not something that affects the sort of observations that we're making, but it's a fundamental problem of theory. Outside of the event horizon, there's a region called excuse me. Sorry. There we go. It skipped over the photon sphere. There's a region called the photon sphere where light can move in spherical orbits. And a little bit further out still, there's this innermost stable orbit. So that's the smallest orbital radius at which material particles can move around the black hole in circular orbits, which are stable. So if you were to perturb them, they would not fall into the black hole. And we need to know what that is, because that actually that region means that matter that's orbiting at that inner radius can persist there long enough to produce enough light for us to see the edge of the black hole. And if the black hole is spinning very fast, then the innermost stable orbit, the photon sphere, and the event horizon are very, very close to one another. And of course, all of this is within the bulk of an accretion flow or an accretion disk. And this is basically a disk of extremely hot plasma, where it's so hot that everything's completely ionized. And you can think of it as a soup of collisionless plasma where electrons and ions move freely. And there's a lot of radiation from these free electrons. And then a lot of black holes, most that we see, the supermassive variety at the centers of galaxies, have relativistic jets. And like I mentioned before, there's two of these, but we just show one here. There'd be one going in the other direction as well. So we've seen a sort of phenomenological picture here now of supermassive black holes, but what about how they would appear? Because we haven't talked about the motion of light. So if we fire light rays around a black hole, you see they get a little bit bent when they pass some distance from the event horizon in red, but when they pass closer, light rays can bend back on themselves. So now let's rotate our field of view, and you see the space-time mesh is actually infinitely curved at the center where the singularity is, and you get all these light rays. And if you fire more and more of them and you approach a sort of continuum limit, you can collect each light ray. You can think of it as like a pixel in an image, and you can fire them all around the black hole. And if you collect it all, you would actually end up with something which looks like a dark circle with an intensity profile which drops off as 1 over the distance squared from the center. And this shadow, this dark region, this absence of light, is the smoking gun signature of a black hole. And we can even consider distributions of matter like accretion disks. And so if you put a disk around the black hole and the spin axis of the black hole is vertical, and you collect light from all regions of that accretion disk, some of that light is bent very strongly by the gravity of the black hole. And so when you actually produce an image, you see something like this. So if you looked at an annulus or a disk edge on around a black hole, you wouldn't see a thin wedge as you'd see normally. So if, like, for example, I have a thing of sellotape here, you look at this edge on, you see just the thickness of it. You look at it face on, you see the ring. With a black hole, you actually see an apparent warping of the rear upper side and the rear underside. And that's actually because the gravity is so strong that the light from those regions you'd never normally see is bent toward into our line of sight. So it's not a physical warping. It's actually a bending of the light. It's gravitational lensing. And the first ever calculations of this that we know of were performed by a French mathematician and astrophysicist, called Jean-Pierre Luminet in 1978. And this is a painstaking calculation, really beautiful picture of an accretion disk around the black hole. And you see it's bright on the left side because that material is approaching us, and it's dim on the right side. This was really painstaking work. Each of these points was a calculation on a supercomputer of the day, and we can run these in, a fraction of a second on a mobile phone today. But these were first done some years ago. And of course, Hollywood has a perspective on this. Many of you have probably seen the film Interstellar, and they have an accretion disk there. And this accretion disk is beautiful, but of course it's not. I always say that it's not quite correct because it's uniformly bright. I should say that the scientific consultant was Kip Thorne, who's one of the Nobel Prize winners for the detection of gravitational waves. And he knew that, and he told the Christopher Nolan, look, the disk will be bright on the left side that's spinning towards us and so on. But they chose to go for this uniform brightness for effect. But so just to say that this isn't an accurate representation, it's too bright. It should be brighter on the left and dimmer on the right. But it's quite beautiful, and it's lovely that they made a film about this. So moving back to physics itself, so what would we see, for example, if instead of having a disk, we just saw background illumination? So if we just imagine like a sky, and we have this starlight behind a black hole, instead of seeing just a nice sort of quasi-uniform distribution of stars in the sky, you'd actually see a very dark asymmetric center here, and this is what we call the black hole shadow. And you'd see this weird blurry ring, and this is called the Einstein ring, and this is actually a lensed ring of emission that would be directly behind the black hole, relative to our line of sight, of a few different stars that appear to be warped into this bright ring, which is very large. And so really this is like a focusing of a very small region on the sky, and that appears much larger than it truly is. And so black holes can really do very strange things with the light that's moving around them. So they actually also vary depending on their spin, so how rapidly they rotate and the angle at which we view them. So for the galactic center black hole here, we have an idea of what this would look like if we had infinite resolution. So this is just one calculation that I did, for example. And we know that as we increase the spin of the black hole, so the bottom left is the actual size of the event horizon, the right is the shape of the shadow of the black hole. As the spin increases, the size of the event horizon shrinks rapidly at the very highest values, and the shadow shifts from being a circle to being actually quite asymmetric with a dimple on the left side. And so you can infer to some extent the spin of a black hole based on the asymmetry in the shadow and the asymmetry in the brightness. And we can calculate curves of this for different parameters. So for example, varying the inclination angle changes the location of the shadow and its aspect ratio, as you can see in these different curves, from a perfect circle when it's looking at the black hole face on in purple, all the way through to looking at it edge on, and that would be the red curve, which is very asymmetric. So that what you see does depend quite strongly on the inclination angle, or rather I should say, it depends to some degree on the inclination angle and on the spin. So how large is the black hole shadow, and how can we do a measurement of this? So if we take these images again, you actually see that the black hole itself is the red circle in the center of this image that's just appeared. So it's not all of the darkness, it's that particular area. And this is where the event horizon of this particular black hole would be. And actually, the region just outside of that is what we call the photon ring. So that's actually what defines the shadow. So what you're seeing in this image on the left is matter swirling in onto the event horizon, you're seeing it getting dimmer because it's being gravitationally redshifted. It's why you never see it touch the event horizon, because it becomes infinitely redshifted. And you've probably heard of this notion before. And it was realized some decades ago, actually, that if you fire light rays, so this image on the right here, all of the yellow light rays are light rays which escape the black hole. So they feel the gravity of the black hole. They're strongly bent by it, but they do inevitably escape. They're yellow. And you actually see a corresponding set in the lower right. So in the bottom right of the image, there's also yellow. It's a bit dimmer, I'm afraid, unfortunately. But you'll see everything which is gray is light rays, which are light rays which are captured. And so what you see in the end is that there's formally, on any black hole image, there's a region which is of the order of square root of 27 times the Schwarzschild radius. This number is exact in the case of a black hole which isn't spinning. There's a finite size. And actually, what this tells you is that if the black hole isn't spinning, the size of the shadow that you see in your black hole image is 2.6 times the size of its event horizon. And we know precisely what the event horizon of a black hole is. We know what its size should be. And so that's linearly proportional to the mass. And so you see directly, by measuring the size of the shadow, have a handle on the mass of the black hole, because the size of the shadow is linearly proportional to the mass of the black hole, and this factor of root 27 in the case of zero spin. So you actually are able to constrain mass, the mass of the black hole, just from the size of the shadow. Okay, so in the last part of my talk, I'm going to talk a little bit about the pathway to imaging both of these black holes and how we did this with the EHT. So there's actually two targets that we've talked about now. So of course we have our galaxy and we have the distant galaxy Messier 87. And the key considerations in all of this are the following properties. So they're both big black holes, but M87 is enormous. It's one of the biggest that we know of. So Sagittarius A star is, of course, our closest supermassive black hole. M87 is very far away at 55 million light years. But if you take the ratio of the mass to the distance, that gives you the angular size. And they're approximately the same angular size. So Sagittarius A star is a little bit bigger, but they're in the same ballpark. So if you have a telescope which can resolve one, you'll be able to resolve the other, which is why we're able to do this. But the tricky part now comes in the visibility conditions. So what are the conditions for the visibilities of both of these black holes? So it turns out that for Sagittarius A star, because we live in our own galaxy at the edge of one of the spiral arms, in the plane of the Milky Way, we have to look through a lot of the interstellar medium, and there's a lot of intervening dust and gas and potentially star formation and all sorts of other processes going on, which refract and scatter and diffract the light coming from the center of the galaxy where the black hole presumably is. We also have to deal with the time variability. So because this black hole at the center of our galaxy is a lot smaller than the M87 black hole, it changes quite rapidly. So there's a factor of 1500 in the mass. So whatever timescale M87 changes on, because Sagittarius A star is 1500 times smaller, things will happen 1500 times faster. And I'll come back to this in a moment, but it's very tricky because it's a very dynamical source. And of course, both of them you have to contend with the Earth's atmosphere, and that's something we have a pretty good handle on, and I'll come to that in a moment. So we actually published the result from M87 first, precisely because we only had to really contend with the atmospheric issues and not with these issues of our own galaxy and the interstellar medium and the scattering and the time variability. So M87 is a much easier source to image, and Sagittarius A star took another 3 years because of these issues. So just to give you a quick sense of scale, so there's a little legend here in the top left, which I won't talk about, but it's the relation between these different angular size scales. You can actually say that the moon, when it's closest to us at full moon, is around ½ a degree on the sky at night. Now, comparing that to M87, which has a diameter of around 40 micro-arc seconds, if you calculate its mass to distance ratio, then that's over 1/90 millionth of a degree. So it's considerably smaller than the moon. It's absolutely minuscule. And the EHT actually gets a factor of 2 better than this. It gets around 20 micro-arc seconds resolution. So in order to get these sorts of resolutions where you can actually resolve the ring of light around a black hole, the shadow, you actually need an array which can essentially, it would be equivalent to you being able to resolve an orange on the surface of the moon with your naked eye from here on Earth. It's an incredibly high resolution thing. And it's a tremendous technological achievement, and that's really what the EHT is doing. It's being able to access these extreme angular resolutions. So when we look at the distribution of the flux from the galactic center, from Sagittarius A star, so the x-axis is basically just the frequency. So these are higher frequencies. So you go from the left, which is like centimeter wavelength radio waves, all the way to the right through the infrared, all the way to X-rays and gamma rays. Actually, the band at which the EHT operates is this narrow red vertical band that you see between the millimeter and the submillimeter. And you'll also notice that solid curve is actually what we call the spectrum, the spectral energy distribution. And the peak of that curve is where the material around the black hole is most optically thin. So you get an unobscured view of what's happening at the edge of the event horizon. So you want to push your observations to get to this submillimeter peak in this spectral energy distribution. And so the EHT is very close to this. So the material around the black hole, it's not completely optically thin. It's a little bit fuzzy, a little bit foggy, but it's translucent. You can see through, you can make out structure, you can discern this, and that's what we were able to do. But on top of this, you also have to contend with the Earth's atmosphere, because the Earth's atmosphere can absorb and scatter this light as well. But it turns out that we're very lucky at these frequencies that the EHT is built to conform to. The Earth's atmosphere has very little transmission. So there's very little, very high transmission. So there's very little absorption by the atmosphere. And this is really important because you need telescopes which are sensitive to radiation, to light, which is not absorbed by the Earth's atmosphere, and which actually gives you a handle on what's going on near the event horizon of the black hole. So in short, both of these black holes are almost completely optically thin at the frequencies at which the EHT is sensitive to, and the Earth's atmosphere is very transmissive to. And that is a very, very fortunate thing. Otherwise, we'd have to put telescopes in space to overcome the Earth's absorption. So we're very lucky that we're even able to do this. And this gives us a fundamental number, which I'll come to in a second. And essentially what you have to do then, because these are millimeter wavelengths, is you have to detect radio waves. So I'm going to show very quickly here a simulation. So a black hole is in the center, and this is a distribution of matter around it. And this is how we build black hole simulations. We actually perturb the magnetic field in that matter, and a turbulence grows, and there's a cascade, and it triggers the loss of angular momentum and accretion of that matter onto the black hole. And over time, the magnetic field gets wound up, and it powers this jet. And there is another jet that isn't shown in the other direction. And if you actually take a microscope and you look at what's happening on an atomic level, what you'll see in this extremely hot plasma is an enormous amount of electrons here in yellow, gyrating around copious magnetic field. These are the blue lines that you see. And as those electrons gyrate around the magnetic field lines, they produce an enormous amount of radiation. And this radiation is predominantly radio waves. So these black holes produce an enormous amount of radio waves. And these radio waves that we need to tune into and detect. And you can actually then determine what the image of the black hole would look like. So this is what it would look like face on. And if we rotate our field of view and we look at the black hole edge on, you see those two lobes. And now, if you recall, they're not physical lobes. It is just like a torus, a disk of matter. But depending on how we look at it, the image looks very different. So the inclination angle is important. So coming back now to the observations, we know that the angular resolution that we can achieve is a function of mainly two parameters. So the wavelength at which we observe the light from the black hole, and the size of the telescope which is collecting this light. And so the ratio of these two gives us roughly the angular resolution. And so we know that the angular resolution, we call it theta, is around 20 microarc seconds for the EHT. So how do we get a 20 microarc second resolution, which we know is required to get on scale smaller than that of the diameter of the shadow of M87 and Sagittarius A star? Well, we know that we are limited by the wavelength of the light that we can detect because of the Earth's atmosphere window. So we're stuck at wavelengths of around 1 millimeter, maybe in the future a little bit shorter as well, but around 1 millimeter. And so this translates into a D, a telescope size. So in order to get this resolution at this wavelength, we would need a telescope the size of 10,000 kilometers, which is completely insane. So we have to build a telescope which is at almost the size of the Earth. which is, around 12,000 kilometers or so. So this is completely infeasible. We can't build a telescope that big. So of course you have to instead do what the EHT did and consider a network of radio telescopes. So you can see that until recently, it was considered fantasy to be able to image a black hole because of this. And it's only really since the turn of the century, around 2000, that the first papers which actually proposed the possibility of doing this began to be published, and people realized that actually maybe we can take an image of a black hole, maybe we can reach these kind of resolutions and have a virtual telescope the size of the Earth. So then how do we do that? Well, what you do is you have different telescopes around the Earth, and you use a technique called very long baseline interferometry, which is a fancy way of recording the data at different telescopes and combining that data and syncing it using atomic clocks. So we get a signal. These are radio waves from different telescopes. And as you know already, for example, you've probably studied physics at school, like Thomas Young and the diffraction patterns of radio waves. You get these interference patterns and fringes from this. And these are recorded at different telescope sites. And the precise arrival times of those signals are recorded because we have atomic clocks. These are hydrogen masers. These are more accurate than, they lose less than a second in 100 million years. They're the most precise clocks that we have. And so we're able to precisely record the delays in the arrival times of the light from the black hole at different geographical locations on Earth. And all this data is stored on hard drives. Now, so essentially what we're doing here is we're taking this network of just 7 or 8 telescopes. They're interconnected. And as those telescopes are pointing towards the source, they're recording data. So telescopes which are further away are recording structural changes on scales close to the event horizon of the black hole. So they're higher resolution. And you can combine different array configurations, so different telescopes within the array, and you get some structure. Now, telescopes which are much closer together pick up more diffuse emission further away from the black hole. And actually, so in a sense, the EHT, as the Earth is rotating, it's basically like a dynamic resolution. So telescopes which are further apart give you higher resolution. Telescopes which are closer together give you lower resolution, so they're picking up structure further away. But you need a combination of all of this. And you can exploit the fact that the Earth is rotating and the telescopes stay pointed at the black hole, that you can build up this picture gradually. And I'll show it in a second how we do that. And this is what we call Earth rotation aperture synthesis, or very long baseline interferometry using the Earth. And we've seen this already. This is the EHT Array Network. And I'm going to skip this movie. So the schematic here is that once you've got this data and it's stored on hard drives, because it's an incredible amount of data, it can't be transmitted wirelessly. It needs to be stored and physically shipped to central locations. So this is in MIT and also at the Max Planck Institute for Radio Astronomy in Germany. And this data is correlated, it's calibrated, these fringes from the diffraction patterns and so on are matched, the atomic clocks are used for this. You can combine this data into a final data product, and through some techniques I'll talk about in a second, you can reconstruct an image from this data, from this radio wave data. So here's just a picture of all of these hard drives being shipped. And you can see it's crates and crates of hard drives, and these are stored on shelves. It's an enormous amount of data. For over 4 petabytes back in 2017 for the 2019 results. So what we're doing basically, if you focus on the central region in this image, the central panel, what we're trying to do is fill all of this white space. So these colored loops are basically the coverage, the UV coverage of pairs of telescopes within the EHT array over the course of an observing night. And so you can think of this UV space as a sort of Fourier domain, so the Fourier representation of an image in terms of visibilities and amplitudes. And basically, you want to cover all of this space. And you can see that we don't get very much coverage at all. It's actually a lot of white space. So we have a very small sample of the possible space of what's happening around the black hole. And we have to basically do like a sort of inverse scattering transform of this UV data to create the image that you see on the right. But you'll see, because the movie is looping, as more and more telescopes join and start recording data, the quality of the image starts to improve. You start to see the bright region get more defined, the dark region becomes darker, and you start to see this proper contrast ratio and so on. And of course, you know, in the future, if we had many more telescopes and longer baselines and we observe for a longer period of time, then we'd fill more of this white space and we'd get a sharper and sharper image, which would be closer to what it actually would look like. And I think I'm running out of time here, so I just want to say very quickly that in 2018, when we were first working with the data, I was also a part of this in team 3. We divided into 4 teams, and here's us in 2018, happy before the start of a very busy week of doing this. This is us at the 4th day, and we've been able to obtain the first black hole image. This is just us in team 3. All 4 teams were able to do this using independent algorithms. We weren't allowed to talk with each other about how we were doing this. And this is us at the end, and we stacked them all together. And this is the average image, which ended up being the one which was published a year later. And so we found these images amongst our teams, which you might say, oh, they look a little bit different. Well, actually, from an image domain analysis perspective, they're incredibly similar and actually consistent. They have a very consistent diameter, ring thickness, the location of the bright regions are similar. You can use the image dissimilarity measures to compare them, and they're very similar. So it's just, you see some extended stuff that seem a little brighter in some regions, but that isn't physical. Those are just artifacts from reconstruction. I could talk about that later, but they're very consistent. And in the end, we looked at the different algorithms. So we have like classical algorithms, we have machine learning algorithms, we have entropy minimization algorithms, and so on. And they all converge on a very, very similar result. And that result gives us a mass which is consistent with previous indirect estimates. And we combined all of these in the image that we published back in 2019. So in the end, though, with this image, you ask yourself, well, what can we learn about the black hole? Well, you can run simulations of the matter falling onto the black hole. So here's one that I made, for example, and it varies in time, and each snapshot in time could be a potential state of the M87 black hole, because this movie is not playing in real time. This is days and days passing in seconds. So it's sped up dramatically. So each snapshot could be a potential state of that black hole. But in the end, when you take a snapshot, and then you blur it to the equivalent resolution of the EHT array. And we don't literally blur it. You consider the array configuration, the different telescopes, and you create an image based on that. You end up with this. And it's incredibly similar to the actual observational data. So it's actually very difficult to discriminate M87's images right now, because the resolution is quite poor. Now, Sagittarius A star is a very different beast. There's many different types of image reconstruction. You see that the morphology of these images just here in this movie, they're very, very different. And I'll return to this point in a second. Sagittarius A star is changing very quickly. So it's far more unconstrained. And one of the reasons for this is the time scale. So on the left here, you see M87. It's an absolutely enormous black hole. And you see the center of this dark region. That's where M87's event horizon is. Sagittarius A star is but a dot in the center of the event horizon of M87. It's absolutely minuscule. As a consequence, you can calculate a dynamical timescale, and you'll see that structure on Sagittarius A star, in Sagittarius A star, changes on timescales of a few minutes. So from over the course of half an hour, you'll see that Sagittarius A star's image structure and brightness changes a lot, whereas M87's changes on a timescale of days to months. So they're very, very different. And you can see this, for example, with just purely ALMA observations of Sagittarius A star. You'll see a light curve here at the bottom, and you'll see the source image itself at the top. And you'll see that the brightness changes by, fact at least 30% over the course of just a few hours. So within the course of one observing night, Sagittarius A star is changing dramatically. So it's akin to Sagittarius A star is really difficult to image. So it's like trying to take a picture of a puppy chasing its own tail through, really blurry, misty glass on a rainy day. Whereas taking a picture of M87 is like taking a picture of a dog just relaxed on a nice clear day. They're very, very different. One is considerably more challenging than the other. And so actually we found with Sagittarius A star, of the millions of potential images that could be reconstructed. So I didn't emphasize this clearly enough, but because the data is very sparse, because we didn't fill all of that white space I referred to earlier, when you reconstruct, there's uncertainty. And so you can create many different possible realizations of what the black hole should look like. And for M87, they're very consistent with one another. But for Sagittarius A star, they're very different. And we found them form into these 4 groups for Sagittarius A star. So the first 3, the green, the blue, and the sort of pinky color, they are all rings, but you see the bright points in those rings are in different locations. So they have 3 different locations for those 3 images. The bottom rightmost image actually are images where there is no ring at all. So it turns out that a very small fraction, on the order of a couple of % of all the millions of possible reconstructions, don't have a ring at all. But when you stack those 3 which do, you end up with the image at the top, which is the one we published. So pretty much all of the images give a ring, and the ring size is consistent. And remember, that size is related to the mass of the black hole, but the structure within the ring, where is the bright blob, it's very uncertain. It could be in either of those 3 locations. It could be in none of them. We don't know. So everything that's within the ring, so the bright features within the ring, are very unconstrained. And I won't talk about the parameters, but for M87, we have a few constraints. For Sagittarius A star, we have many, many constraints. And I'm not going to talk about these now because we're out of time, but you can refer to them later or ask me more. There's a lot of constraints on our modeling. So we can construct libraries of simulations to compare with these actual observational data and learn something. And what we find in the end is, don't worry about anything here except green with no hashing. So it's actually just the rightmost 2 and the bottom right of these. There's only a few models of all the millions of models that we performed that actually can match the Sag A star data and satisfy all of the different observational constraints. So unlike M87, Sagittarius A star is actually highly constrained, and only a few models survive. And those models, which we call best models, tend to favor viewing inclination where we're looking almost face on. The magnetic field is extremely strong. The black hole is spinning fast and in a positive sense. So the disk and the black hole rotate in the same direction, and they're accreting matter very, very slowly. So they're feeding very slowly. And if you actually look at the data themselves, so the horizontal axis, you can think of this as the separation between telescopes. As you move to the right, those are pairs of telescopes which are further and further apart. So on the left are telescopes which are much closer, so they're picking up structure, over the whole image. And as you move to the right, they're picking up structure closer and closer to the event horizon. You see that for M87 here, these colored points, they're just clusters of the different observations for pairs of telescopes. They all cluster around this gray dashed line. And this gray dashed line is actually the Fourier transform of an annulus. So basically a ring of a particular thickness. So you can see that the data actually have a ring in them. It's not like we impose that, or it's an artifact of the reconstruction. The data actually form a ring. And that ring is a prediction of general relativity. And we get a constraint on the size of that ring to be around 46 microarcseconds in diameter. Whereas if you look at the Sagittarius A star data now, they're a mess. So as you move to the right, so this is pairs of telescopes which are further apart, you'll see that the error bars on these, like the brown and the pink and the green points on the far right, so these are telescopes very far apart from one another, the error bars are so huge that data is basically completely unconstrained and unreliable. So actually this shaded red band with the thick red curve inside, these are the only ranges where the data is reliable. So you can see that although you can try and fit a ring to this, you can get a good fit to the diameter of the ring, because that's where this gray curve drops to 0 quickly. You don't get a good constraint on where it dips again at around 6.5 or 7 gigalambda on the x-axis. So that's telling you that the thickness of the ring and what's going on inside it is very poorly understood, and we don't actually know. And so you can see that the time variability of Sag A star is reflected in these data points on the far right, where the structure near the event horizon is changing so rapidly that we can't shrink those error bars yet. Okay, you can compare the 2 black holes, and if you put a ruler next to them, you'd see the left one, M87, that's a length of 10 to the 16 centimeters. That's enormous. And Sag A star, it's around 6 times 10 to the 12 centimeters. So it's 1,500 times smaller, but morphologically they're very similar. So you get this central blue circle, which is actually where the event horizon is. So they're a regime where gravity is dominating here. So even though the time scales and the mass scales are very different, the image structures are very similar, because general relativity dominates, gravity dominates. Now, I'm wrapping up. This is my last couple of slides. The first thing that we've learned from all of this, and this is really the key question, really, as astronomers and physicists, we've actually been able to do a really beautiful test of general relativity with these new Sagittarius A star data last year. So we've actually been able to compare millions of different models and even vary the theory of gravity that describes the black hole. And we found that the diameter of the ring from our observations is around 63 million kilometers with an error of around 2.8 million. And the prediction from Einstein's theory of general relativity is that the diameter should be less or equal to 63.4 million kilometers. So we're right in the middle of what the theory predicts. And this is just, you know, and there's no messing around with data here or anything. It's just comparing the data with, you know, with the theory. And this is really quite beautiful. It's telling us that so far, general relativity is doing really well and it's passing these tests. And this is wonderful news for Einstein, and it's frustrating as physicists because we're not quite at those scales yet where we're able to see any obvious deviations from general relativity. So far, these observations are entirely consistent with general relativity. So we've learned a lot of things. We've been able to get a mass of M87 that's more accurate than previous constraints. We've been able to measure the contrast ratio in the flux and establish that central brightness depression is consistent with an event horizon and not a wormhole or some other exotic compact object. These results are actually consistent with general relativity. We know that the shadow size and shape are sensitive to the space-time geometry, and as these measurements improve, we'll be able to constrain things like the mass and spin much more tightly. There's a lot of ongoing and future work. In short, we're able to use the polarization of the light to learn something about the magnetic field structure around the black hole and probe the conditions of the matter there. We're pushing to shorter wavelengths, which will make the ring thinner. So we're actually able to get much tighter constraints. Some of you may have even seen a paper just a few days ago on this. And we're going to put telescopes in space so we can extend those baselines and get much higher angular resolutions and even make movies of black holes. And so I thank you for hanging on in there. I think I've overrun a bit here, but I just wanted to say that it's the end of my talk, but this is the beginning of an exciting new field of astronomy, namely of imaging black holes and studying what's happening on the scale of the event horizon. And in time, we'll be able to resolve the structure that's changing around the event horizon, maybe a little bit more like this. So I end with a movie of what the galactic center supermassive black hole would look like. So every second is 2 minutes of real time in the galactic center. And this is what it would look like, assuming our present constraints today. And hopefully one day we'll start to see things a little bit more like this. So thank you very much for your attention.